In this video, we'll discuss an early application of attention for improving sequence-to-sequence models with encoder-decoder RNNs. This helps to understand the concept of attention in detail before we see how it is used in transformers nowadays. Let's dive right in. Improving RNNs with attention. So before the current dominant transformer architectures, the best methods for many tasks in natural language processing were gated recurrent neural networks, such as the LSTM or also the GRU. One exemplary language task is neural machine translation. In neural machine translation, you translate a sequence of words in one language, such as French here, into another sequence of words in another language, such as English here. And classical sequence-to-sequence models actually sequentially read these inputs and sequentially produce outputs. Now this is useful because in this case here, for example, the French sentence has only 3 words, je suis étudiant, and the English sentence has 4 words, I am a student. And you couldn't have a one-to-one mapping of the French words to the English words, but you can sequentially read in the inputs, put that all into sort of one context, and then sequentially output all the outputs. And that's what these sequence-to-sequence models do. Now we have some really cool animations of this and of many other concepts in attention and transformers, and I would very much like to thank and credit Jay Alamar for creating these animations and allowing us to use them. So if you animate this, it looks as follows. You sequentially read these inputs and then sequentially, one by one, output these outputs. Now in a bit more detail, these sequence-to-sequence models typically are composed of an encoder and a decoder. The encoder is often an RNN and processes the input sequence into a so-called context vector. And the decoder, which is also often an RNN, takes this context vector and then produces the output sequence. Again, in an animated form, this looks as follows. You take in the inputs in the encoder, then you produce the context, then you move the context in the decoder, and sequentially compute the outputs. If you look at this in a little bit more detail, you see that the context that is moved from the encoder to the decoder is actually just the last hidden state of the encoding stage. So you have a hidden state here after the first stage of the encoder, you have a hidden state here after the second stage of the encoder, and the last hidden state of the encoder, that is actually the context that is moved into the decoder. Again, if you animate this, it looks as follows. So you read in your words one by one, you compute the hidden states go into the next encoder stage, and here now this hidden state 3 is moved into the decoder. The decoder also has an internal hidden state that is not visualized here. The disadvantage of this approach is that there's one vector, namely this last hidden state of the encoding stage, that has to encode the information for all the inputs. So the entire sentence has to be encoded in this one vector. And this is where attention comes in. The idea of using attention is to use all the intermediate states, the intermediate hidden states of the encoding stage, and pass all of them on to the decoder RNN. And the decoder can then learn to focus on the relevant input vectors from the encoder, the ones that are relevant for the particular word it's currently outputting. So again, in an animated fashion, this looks as follows. You read your words one by one, compute your hidden states. The hidden states move to the next encoder stage. And then at the end of the encoder, you take all the hidden states from the previous encoding stages, move them to the decoder. And the decoder at each step now is an attention decoder that can actually look at all of these 3 different hidden states of the encoder and actually compute attention to each of these individual states and pick the ones that are relevant for the current word being produced. In a bit more detail, the decoder attends to the part of the input, the part of the encoder hidden states that are relevant to the current decoding step. It does so by computing a score for each of the hidden states that it received from the encoder. And this score depends on the similarity of those hidden states of the encoder to the decoder's current hidden state. And what the decoder then does is it multiplies each of the individual hidden state by this score, in particular by a softmaxed version of the score. The softmax is just to actually focus mostly on the state with the highest score and to actually have these scores sum to 1. And so this amplifies the hidden states that have high scores, so that are the most relevant for the current decoder's hidden state. And it drowns out those hidden states that have low scores. Let's look at this in an animation. So we're currently at the first decoding step. We have time step 4. We have 3 time steps of the encoder. And each of these encoders has a particular hidden state. And then the decoder has a hidden state that is here. And now this hidden state is going to be compared to the encoder hidden states one by one. And a similarity is going to be computed. So we've now computed a similarity score for each of these hidden states. Here we have 13, 9, and 9. And these scores, those are the attention weights for this current decoder time step number 4. What happens next is that we compute a softmax. So we simply take e to the power of these scores and then normalize, so we sum to 1. And then we multiply each of these original vectors here by these softmax scores. And then we simply add these softmaxed vectors in order to get the sum of these vectors. That's going to be the context vector for the decoder at our current time step 4. So let's look a little bit more in detail what happened here. We have this decoder state here. This is most similar to this particular state here. It's not that similar in terms of the visuals here, but well, this is the most similar. And so this gets the highest score. It then gets by far the highest softmax score. The other 2 states get almost drowned out. And this vector here then is going to be very similar to this vector with some small additions coming from this vector. And so that means at this decoding stage here, our context is mostly going to be dominated by this input H1. All right, now we will look at a worked example from the literature where this type of attention mechanism was used for one of the first times. This original paper here is by Benjo et al., and it used a so-called bidirectional recurrent neural network. In this bidirectional neural network, there's no magic going on. It's just an RNN that parses the input sequence from the front to the back. That's this part here. And then there is an RNN that parses it from the back to the front using exactly the same RNN equations. And you get a representation that has these forward arrows and a representation that has these backward arrows. And this concatenation of these is going to be our representation of this first input. So that's what the encoder does. It encodes our input somehow. The details here are really not important. You have a H1 hidden state for this input 1, you have an H2, you have an H3, and all the way up to HT for the last one. And so that's what the encoder does. And the decoder, well, we have run this in this case here already for t-1 steps. And what we're interested in now is how do we compute the output for time step t? And we want to actually use attention in order to look at our hidden states from the encoder. And we do that by, well, actually computing a softmax, and we will look at each of the individual steps one by one. So the notation here is not that important. What is important is that at each step j, we have a representation that is the hidden state. And this hidden state happens to be this concatenation of the forward RNN and backward RNN encoding. Now we compute a score for each of these encoder hidden states, hj. This depends on our current decoder hidden state as t-1, and it depends on each of the individual hidden states. So this is one computation that happens. We use, in this case, a feed-forward neural network for this. This feed-forward neural network gets these two inputs and outputs the similarity between the decoder hidden state as t-1 and the encoder hidden state h1. And we do that for each of our encoder hidden states to get these E sub tj's. So t is for the current time step, and j is for the encoder state j. And then, well, we just compute the softmax over these E values, and we call the result alpha sub tj. And this alpha sub tj, that is the final weight, the attention weight that is given to each of the individual context vectors and is multiplied with them, and we sum over all the different encoder states to get our context. And this context is then being fed into this recurrent neural network here, which happens to be a GRU in this particular case. And the previous decoder state is also fed there. And it also depends on the previous output, y t-1. And voila, there you have your inputs to this GRU, to this particular type of recurrent neural network that used attention to the different encoder hidden states in order to focus on the right parts of the inputs at this particular point in time. And what were the right parts of the input was determined mostly by this current hidden representation of the decoder S sub t-1. And this brings us to the end of this lecture. And as always, I'd like to leave you with some questions for you to activate the material. I'll see you in the next video. Thank you.